Let's now come to our numerical. Let's now use the numerical method in our Matlab. Okay, I already have prepared here our initial code for this, which you'll be editing. Okay, so let's have this one. So for our numerical, we'll be using this one. So that's why we have G, the drag coefficient, then the initial values, T init and V init, then the T final. We also have the step size for this one. Okay. Now, I already have discussed this one. Then, okay. So this is this dvdt. This is it. It's the slope. So you're calculating the slope by this. Then this one is actually this one. Then so if let's say you want to calculate for v at 10 seconds, so this means this is v at 8 seconds plus dvdt times delta t, so that will have the incremental value for our v. So that will be our, in that way we'll have v at 10 seconds, and that v at 10 seconds is actually that 10 seconds is actually this one. This time is 8 plus 2. That's the time here will be equal to 10. Okay, let's try this. Let's save this as numpara. Okay. Wait. Okay, so we have here for our step size of 2, this one. So 19.6 at 844.82, 49.96. Okay, so that's correct. Now, what if we try to have a step size of 0.1? Now, before that, maybe you have noticed that I haven't used the input command, because as you have observed in our previous video, using the input command while debugging would delay our work. So that's why let's just insert the input command when we are when we are almost done. Okay, let's try for 0.1, a step size of 0.1. Then maybe let's just choose 6, because it's just to minimize the number of rows. At 216.53. Okay, this one, yes, that's correct. At 4, 27.94. Okay. At 6, 35.822. Okay, so the values are correct. However, you can observe that V at 6 seconds has been displayed twice. So why is that so? Let's try displaying, because probably ng mata na ang mga lamok. We know that our program will terminate, this loop will terminate if dt is equal to 0. Now at time equal to 5.9 plus dt this will be 6. We're already done with v at 6, so this will be 6. Yes, that's correct. Then is dt equal to 0? No, not yet. And you come here, dt will be 0. Then you print this one. And dt is already 0. Yes, you print this one, so okay, so this should be 0. That's why it repeated. How about we transfer this one here so that after dt becomes 0, then it will no longer calculate this as a v and a t. Okay, let's try. It still won't v6 is still here. Let's try to display dt. Okay, so as we can observe, at v6 dt is very small, this one. So that explains why at v, okay, let's say at 5.9 here, at 5.9 here, so at time equal to 5.9, so v will be, here will be v at 5.9 plus dv dt times dt in order to get the velocity at 6. Then this is 5.9 plus dt, so this will be 6. When we come up here, though that is 6, however, the time during at this iteration is actually is not 6 actually, but very close to 6. That's why at this iteration we have the difference between t final and time, that the t final is 6, as seen here. T final 6 minus time is very close, however time is not 6, so that's why we have a dt that is very small. It's only up to, so that's why this won't be satisfied still, so it goes on in calculating this one. So that's why we have an extra b6. So why does this happen? It's because our computer has a limited capacity in representing numbers, so that introduces an error, and it's that error, that's why we have this, supposedly we have 0, but we have this very small number. So in order to solve that, instead of using dt equal to 0, let's just use dt is less than or equal to a very small number. Let's say that one. Okay, let's try this. Okay, so v at 6 is just displayed once. So let's now take this away, and okay, let's try this once again. Okay, good. So v at 6, we're using 0.1 35822. Okay, yes, it's 35822. Now this time let's make a function. Maybe you can observe that this entire block is actually the one doing the Euler's method. So instead of placing it here in our main, how about we make a function that will do the Euler's method, right? Okay, so for that we will call that function here, that function Euler. Then let's give to it the inputs for, maybe we need the, okay, let's have mass, then the drag coefficient, let's have the initial time, the final time, Maybe let's have it here, the step size. Then the V na siya. Okay, then let's make a function. Let's name the function Euler. The following inputs will have mass for mass. Let's have drag coefficient. Okay, let's have C. Okay, let's be consistent. Let's make this C. And then step size, let's make this step size H. DI, DF, BI. Okay. For the mass, okay, I forgot to. Should be this one. For the drag coefficient, this will be C. Then for the step size, let's have H. Oops. Let's have H. Then for okay, then now let's have B. So be TI, and this will be TF. VI. Let's have V. Let's also make a function for our slope. So our dv dt here will just be equal to let's call a function. The function cm. Okay. Okay. And then let's have so we won't be using that. Let's have a function with output variable slp. No. Having the name slope with okay, let's also have this as mcv. Okay, just to remind again that though these are of the same names, however this m and this m is different because this belongs to another function. This m is seen only in this function, and so also this m, it's only seen in this function. And then let's SLP is equal to this one. Times V. Okay. So we now have, okay, an end statement is missing. Okay, let's try this. Wait. Okay, it's fine. Unrecognized variable, line 9. Should be like that. Let's have this unrecognized variable G. Okay, G is, we use G here and we don't use it here. So this one, let's just transfer this to this function. Okay, let's try T final in line 16. It should be TF. Okay, so this is at 0.1635.822 at 427.94. Okay.